Good morning, students. We've got two warm-ups here for you. This might take a couple of minutes to work through, but these are really good ones to work on, and we're looking for the particular solution to the differential equation. Here's the differential equation and the initial condition that's given. So go ahead and work on these two. Press pause in the video, and then I'll go over it shortly. Let's go over number one here. The very first thing you have to do is separate the variables. So this y has to be brought over to the other side. Now notice this is 4x times y. So I'm going to divide both sides by y or times the reciprocal. So I got 1 over y dy on the left side and then 4x dx on the right side. So we're going to take the integral of both sides, and the integral of 1 over y is the natural log of absolute value of y. And then the integral of 4x, remember we add 1 up top, so I'll get 4x squared, but if I put a 2 up top, I got to divide by 2, and then plus c. Do not forget the plus c. A lot of times, students forget to put it right away, and they remember at the end. Well, forgetting it here is an error, and you got to be careful on that. So what do we do now? As soon as the c appears, we're going to use the initial condition 0 and 3 and plug that into the spot for x and y. And then use whatever algebra you need to solve, but I end up with 0 plus c, or c equals ln of 3 equals c. All right, well now we go back to the spot where c was first present, and I'm going to plug it in. So I have everything written exactly the way it was, except for 4 over 2 is 2. And then I have ln. So now, once we get to this point, it's solving for y and doing whatever we need to do. In this case, I have to take the natural log of both sides. And when I do take the natural log of both sides, e and ln will reduce out, and I'm left with the absolute value of y. And then here we get e to the 2x squared. And this is that special pre-calculus property that when we have addition, we can rewrite that as e to the natural log of 3. And I don't need the absolute values here because that is positive 3. And then it becomes multiplication. When they each have their own base, you multiply them together. And the reason why we do that is notice the e and the ln reduce out. So then I'm left with y, the absolute value of y equals, and where would that 3 go? It's multiplying, so I would put the 3 out in front and then do e to the 2x squared. And that's about as far as I would go, other than now I have to think of the absolute value. Well, which value is this going to be? Is it a plus or minus? And it all depends on the output. So think about when x equals 0 goes in. If I put 0 here, I get 2 squared. 2 times 0 squared is 0. So e to the 0 is 1. So I'm left with a positive 3. And I want this answer to be positive 3. So that means that this value is just the positive answer and not the negative side of it. Okay? Now, if this was a negative here, then this output would be negative, so I would use the negative value. So that's why we check the initial condition in our answer. But there you go. There is the particular solution for problem number 1. Okay, so go ahead and I'll pause it. I'm going to get started on number 2. Remember, the very first thing you need to do is move this e to the y over to the other side. So first thing I'm going to do is divide by e to the power of y. But remember, that would be 1 over e to the y, which we would prefer to have it written as e to the e to the negative y. And then the dy stays, dx is brought over with the x squared, and now we're going to do the antiderivative of each piece. If you want to use u substitution here, you can, because this negative is going to come into play. But if you've done it often enough, you know that there would just be an extra negative that you have to compensate for. So be careful of that negative. That's a very common missed problem. And then this one, we're going to add 1 up top. So I'll get x to the 3rd, but if I put a 3rd power up top, then I have to compensate and put a 1/3 out in front. So now the c appears, and as soon as the c appears, we're going to go right to our initial condition, and we're going to plug in 2 and 0. So we have negative e to the negative 0. Negative 0 is still 0. E to the 0 is 1. And then this negative will just ensure everything is negative 1. 2 to the third power is 8. 8 to the 1/3 is 8/3. And then if I'm going to subtract, I want to think of negative 1 as 8 over 8. And then I would subtract an 8/3. Oh, sorry, nope. That should be a negative 3 over 3 because I've got a denominator of 3. So if I subtract the 8/3 over here, I have negative 3 over 3. That's going to combine together to give me negative 11/3. Not super friendly, but there it is. That's C. So what do? We go back to the spot where C was first present. I'm going to replace this C with what we found the value to be. And now we're going to solve for y. The one tricky thing here is, so this negative, we're going to divide everything by a negative. So it'll give me a negative 1/3 x to the third, and then a positive 11/3. And then I have e to the negative 1. So I'm going to rewrite it. Assuming e to the negative y, I'm going to rewrite it as 1 over e to the y. And the reason why is because I want the y value to be in the numerator. So if I make the right side a fraction by putting it over 1, I'm going to flip both sides. So I get e to the y, and then that's going to flip everything upside down. That's called the reciprocal property. Take the reciprocal of both sides. And then our very last thing is to get e of the y by itself, and the only way to do that is to take natural log of both sides. So I get e and ln reducing out, leaves me with y. And then my final answer, I'm not going to simplify it anymore. Is right here. Okay. A good idea, if we have time, is plug 2 back in. If you plug 2 in here and you simplified, you end up with 0. Okay. Does your output equal 0? So you check your answer. And really quick, if we do part of this in our head, if I plug in 2 here, 2 cubed is 8. 8 times negative 1/3 is negative 8/3. Negative 8/3 plus 11/3 is 3/3 or 1. So I get 1 over 1. So all of this, if I wanted to check, everything in the middle would end up being a 1 over 1 or 1. And then I get the natural log of 1, which is 0. So I just kind of used that initial condition and checked in my head, but notice I get y equals 0, which is exactly what it should equal when x is 2. All right, so you can pause it, make sure you understand all that. We've got 2 things to do today. We're going to look at more separable differential equations, but these ones involve U substitution. So we're just building on those skills we already know. And then we got something fairly new, but it's a connection back to Algebra 1. So, quote for today: if you aren't in the moment, you are either looking forward to uncertainty or back to pain and regret. By Jim Carrey. All right. You could totally do this one on your own right now. I'll just give you a hint. It may involve U substitution. So find the particular solution. I have my differential. I need to separate anything with x's and y's. But notice this one's a little tricky. So if you feel confident, hit pause. If not, we're going to go over it. So the tricky part here is to remember what this property is telling us. I've got y, e to the y plus x. Well, that can be rewritten as e to the y times e to the sine x. And then we've got the cosine x just waiting out there. So it's technically the first step is just rewrite using the properties of exponents. And now, which is the one with the y? Well, it's this e to the y that I'm going to divide over to the other side. And when I do that, it's like having, just like the problem we just did, this will be 1 over e to the y, which is better written as e to the negative y. And then I have cosine of x times e to the sine x dx. All right, so now we can integrate both sides. Here again, you have your u substitution. So the antiderivative of e to the negative x, e to the negative y is e to the negative y, but there would be a negative we'd have to compensate for, and you could do u substitution to see where that negative comes out. Over here, I might actually show the work for u substitution. Because look at, we have sine x is in the exponent, so if I let u equal sine of x, then du, the derivative of sine of x, is cosine x dx. Which, notice, here's my cosine, here's my dx. This cosine and this dx are going to be substituted by just writing du. And then the only thing that's left is e to the sine, but that's e to the u. So we have u substitution really cleans this up and makes it look kind of nice. Of my integral of e to the u, and then again, du is going to replace cosine and dx. So this is a much friendlier integral. If you realized it and you could do u substitution now in your head, you don't need to show any of this work, and you could just say the antiderivative of e to the u is e to the u, but then we know what u is, right? U is sine of x. So you could go from here right to here very quickly, and then just don't forget your plus c. All right, so where are we at now? The first instance where c occurs, we're going to go right back to the initial condition. We're going to plug it in. Let's plug in x equals 0 and y equals 0. I plug in 0 for y, 0 for sine. Well, this becomes negative e to the 0, which is negative 1. And this becomes e to the sine of 0 is 0. So we get e to the 0 is 1. And then if I move this negative, or this 1 over with subtraction, I end up with c getting to be negative 2. Go ahead and pause the video if you need to, if you're not confident on where that came from. You can follow the steps. But now that I know c, I'm going to go right back to the spot where c first appeared. And we'll plug in c equals negative 2. Now it's just algebra time. We got to solve for y. First thing I'll do is get rid of the negative by dividing all sides by a negative. And then you can see instead of having e to the negative y, this is where I rewrote it. So now it's 1 over e to the y, just because I don't love the fact that that negative is going to come into play. So I'm going to reciprocate that, which you don't have to. You could do this other ways. This is just one method of doing it. So I'll reciprocate both sides, and this should go all the way over. So that gives me e to the y equals 1 over negative sine of x e to the negative e to the sine x plus 2. And then the last step, I have an e, so I have to use the natural log of both sides. And that will give me y equals the natural log of 1 over negative e to the power of sine x plus. And again, if you take your values, take the x is 0, do you get y? So if you plug in 0 here, you should get the same answer here as you simplify. Everything should work out perfectly. All right, let's try another one. This one's just a little bit more unique. We really haven't seen something like this before. Our goal is to separate the differential equations. If you're feeling confident and brave, go ahead and pause this and try it on your own. If not, I need to separate the variables. Notice the only thing that has a y in it is right here. Everything else is perfect where it is. I need to just divide by the square root of y. So when I do that, I'll get a 1 over the square root of y dy on the left-hand side. And then I have a 4 natural log of x over x dx on the right. And our job then is to take the antiderivative of each. Remember that 4 is a constant? I can pull that 4 to the outside and just treat that as a constant. And you might recognize this one. If not, I'm going to rewrite this because I don't love the square root of y. Remember, that's the same as y to the 1/2. And since it's in the denominator, I could just rewrite 1 over the square root of y as y to the -1/2. That's going to help me a lot with doing the antiderivative. And then another way to think of this one, which might help you out, is the divide by x can be rewritten as 1 over x. So notice these are equivalent. And the reason why I show that is that might help with u substitution. So if you're feeling confident, pause it right here and find the antiderivative of each one. What I'll do is I'm going to undo the power rule by adding 1 up top here. Notice I put 2 over 2 as that creative form of 1. So this turns into y to the power of 1/2. When I put a 1/2 up top, I have to put the reciprocal out in front, so I'll put a times by 2. And then over here, I'm going to do a u substitution. And I'm going to let the natural log of x right here be my u value. The reason why is look at what appears when I take the derivative. The derivative of ln is 1 over x dx. So this 1 over x dx is going to be replaced by du, and then the natural log of x is going to be replaced with u. So u substitution will allow us to turn this integral into something that looks a little bit easier. Okay. Now remember, this is technically u to the first power. So if I'm going to undo that power, I have to add 1 up top. The 4, remember, is a multiplier. And then I'll get u squared. Let's do that in red. So 1 plus 1 is 2. I'll get u squared as my antiderivative, but if I put a squared up top, I have to compensate and put a 2 out in front. And then don't forget about your plus c. Notice, as soon as we get that plus c to appear, I'm going to go to my initial condition, and we're going to plug that in. I should actually replace, I almost jumped the gun, I should replace u with the natural log of x first. So let's do that. And as I'm writing this, 4 times 1/2 is 2, so we can clean that up. And then the u is going to be replaced by the natural log of x. So now I'm going to plug in my initial condition. All right, we know y is 1. That's pretty friendly. And we know x is e. That's also pretty friendly. So when y is 1, x is e. And now it's just simplifying to find c. So 1 to the 1/2 is 1. 1 times 2 is 2. the natural log of e, remember those are inverses of one another, so whatever e's exponent is, which is 1 if it's not written, they go away and the exponent is left over. So then 1 squared times 2 is 2, subtract 2, and we end up with c equaling 0. So now we're going to go right to the spot where c first appeared, but I didn't take this one because this was written in terms of u. I want it written in terms of x. And you don't have to put the 0 in there because that doesn't help us at all. So I'm going to just kind of write it, but assume that it's gone. And then our job is to solve for y. So I would divide all pieces by 2. I'm not even going to write the 0 here anymore. And then the next step is, how do I get rid of the 1/2? Remember that 1/2 is the same as the square root. So the way we get rid of this would be raise it to the reciprocal power, which is just raising it to the second power. That leaves me with y equals the natural log of x to the 4th power. And I would stop right here. I would also check what happens if x is e. When I plug this in, I get ln of e is 1. 1 to the 4th power gives me 1. So I checked my initial condition. The signs work out, the values work out, and everything is good. So those are how you do some separable differential equations. The key is you have to separate the y first. And then you're going to do whatever integration methods we have taught you. U substitution is totally fair game. And you use the initial condition to find c, and then plug c back in to find the particular solution. All right, I got a special one for you here that I want you to try. And I'll give you one hint because this is kind of tricky. P prime equals k times p. Now what this means is the rate of change of p is proportional, directly proportional to the amount of p present in itself. And that's may ring a bell, may not. The only hint you have to remember is when we solve a differential equation, we need this to be written as a differential. So let's pick, sometimes they give it to us, but let's call this PT, dp over dt. So we're taking the derivative of p with respect to time. So we talked about that before, but remember that's how we can rewrite this. Now remember, k is a constant, so that's like a number, so you're going to leave it. All right, well, we have to separate before we can do it. I have a p on this side, and I have dp over here, so I need to divide by p, and then we're going to leave k because it's just a constant, and move the dt. Now we're ready to take the antiderivative of each side. And there it is again. Hopefully you're getting really confident whenever you see 1 over a variable. It's a single variable. If it had an exponent, we'd have to do it differently. But if it's linear on the bottom, it's just the natural log of whatever that is. And then remember, k is a constant, so the k can float outside here. So this is kind of like a 1. So whose derivative gives me 1? It's t. And then the k is the multiplier. And then we're just going to put plus c. Now they didn't give us any initial conditions, so I have to just solve for p. I'm going to take the natural log of both sides. Running out of room, so I end up with the natural log and e reducing out. So I have the absolute value of p is equal to e to the kt, and then remember this power of e, I'm going to say times e to the c. Now, this might not look super special right now, but remember, c is a constant, right? And so is k in this case. K is a special constant we'll talk about. But e to the c, what if I let e to the c equals a? And what does that mean? It might even call it a of 0. That means it's the initial amount of substance or whatever we're talking about present. So watch what happens if I rewrite this and I call e to the c a of 0. Now the absolute value is going to just put a plus minus out here. So p is equal to the absolute value of a of 0 times e to the kt. Wait a minute. Haven't we seen this before? If I change a couple letters around, remember the PERT formula back in algebra? P was the initial principal, or in this case, A is the initial amount. E is our base, R was the rate, and T is time. Well, K is a constant that is proportional to the amount of substance total, and that's our rate. So what we've just kind of discovered in doing this problem is, you know what? This model right here can represent exponential growth and decay. It's an exponential model. Now, the special part here is knowing that this model right here is now written as an exponential model. It could be growth or it could be decay, and I should have just put exponential model, not growth here. But what is it? The rate of population is changing directly proportional to the population amount, the initial amount. Well, what do we know about a couple of these items? K is our scale or our constant of proportionality. Well, K is like our rate, right? So this K value here, if K is positive, then it's going to be an exponential growth model. If K is negative, that means the function is decaying over time. So if you do the differential equation, you end up with this value and you have K as an actual number, you know if it's growth or decay based off of if K is positive or negative. And remember, K is the same as our R in the PERT value. So if you like the PERT formula better, relate back to that. A is the initial amount, and T is time present. Okay, so hit pause. I would kind of write this down just so you get it. But let's look at a couple examples here of how this is present and how you can actually save some time. If you see that a rate of population is changing proportional to the population itself, so if a rate is changing proportional to itself, then you automatically know that it is an exponential model. So you can just think of the PERT formula or the way we wrote it here. Okay, so this is just kind of our, you don't have to write this, but just what you said, the rate of change of a quantity is proportional to the quantity itself. So if I have y, this is the change in y is proportional to itself. So it's changing with proportion to itself. Let's look at an example here. What's your goal when we have word problems? You want to translate the words into a differential equation, define your variables, and then solve by separation, or if you recognize there's that pattern, you can do that. So let me show you what we mean by this problem right here. Bacteria in a certain culture increase at a rate proportional to the number present. So right there, that term is you have to kind of really pick out what's going on. So bacteria in a certain culture increases, so that increases is going to tell me that this is exponential growth. All right, something's acting weird with my pen. Now I know that for a couple of things. It's because the rate, remember rate is the derivative, and then they don't say is, but is would be equal to, so the derivative is equal to or proportional to the number present. When you see proportional, that means you have to have that k value, and then we have the number present. So let's call B the number present of bacteria. So I have the derivative, which would be the change in B with respect to time, is equal to or is proportional to K times B. Remember, proportional or directly proportional meant multiply. Well, now, if I do the same work, it's a differential equation. If I do the same work and solve all of this, B would come over here. The K is a constant, and time would be over here. Now, you're going to recognize all this work that we just did is the same thing we did on the last slide. So if you recognize that, you can skip this work because you recognize the pattern, and you can jump right to the PERT formula. Okay? If not, then you would do exactly what we would do here. Take the antiderivative. This ends up being k to the t plus c. And then we're going to raise both sides to the power of e. So we end up with the absolute value of b equals, and I'm going to skip this e to the c is really like the a value, and then kt. So there's my PERT formula. And now we just have to pick out the information that we know. Right, so here's my exponential model. Which what I'm talking about is if you recognize that it's just proportional to itself, the amount of bacteria is proportional to itself, you can skip all this work and just write the PERT formula. Okay? Take some practice to get really good at that. But now, what do we know? If the number of bacteria doubles in 3 hours, how many hours will it take for it to triple? So here they give us the initial amount. Now they say the amount of bacteria doubles in 3 hours. Well, let's think about that. If I don't know the amount that was there originally, so I'm going to leave this A as the initial amount. Okay, so B is equal to the initial amount, e to the kt. Now I don't know what k is, right? I don't know what that rate is, but I know that it took 3 hours to double. Now the question is, what is this B value? Well, the B is the amount of bacteria that's left after 3 hours. Well, it's double whatever A is. So if I have A as the initial amount, then this is double whatever A was. And you're going to notice something here which is kind of interesting. We don't have to know how much bacteria there was to start because A is just a constant. So when I divide both sides by A, that goes away, and I'm left with 2 equals e to the k times 3. And then it's just algebra. Solve for the missing pieces. Right? I got to solve for k. I need to find that rate. Well, what do? I got to get rid of e. So I'm going to take the natural log of both sides. So I get ln of 2 equals the natural log and e reduce out, so that's equal to 3k, or you could write k times 3. And then to get k by itself, we're going to divide. Now remember, k is my rate, right? Notice it's a positive. Because this is positive, that means it's increasing, or that just confirms that this is definitely a growth model. Well, what do? Now I got to find out how many hours will it be when the bacteria is tripled. So I got to go back to the spot where K was first present, which is really here, and now I know what K is. So I'm going to rewrite my formula. except for with k, we're going to write k as the natural log of 2 over 3 times t. But how many hours? So we got to solve the final problem. How many hours will there be for the bacteria to triple? So what does that mean this value has to be? If the initial amount is A, for us to triple that initial amount, that's going to be called 3A, right? That's 3 times the initial amount. And as we learned, we're going to divide by it. So the A doesn't matter, but we know that that is 3. And then we just have to solve for T, knowing, because T is the amount of time, that tells us how many hours, knowing what the value of K is. So now it's just quick algebra. I divide both sides by A, that reduces the A's out. And you'll notice it's similar to what we did before, except for now we're finding T because we know K. So I got to get rid of base E, which means I'm going to take the natural log of both sides. So E and ln go away. I'm left with the natural log of 2 divided by 3 times T. And then I have to divide by this whole piece. Well, I don't like division, so I'm going to multiply by the reciprocal. I'm going to multiply by 3 natural log of 2. And then this leads me to a pre-calc property, but to be honest, I would just grab my calculator at this point. We could write this a little bit differently, but this is the answer. They want to know how many hours. So what I'm going to do is actually do this problem in my calculator and do 3 times the natural log of 3 divided by the natural log of 2. And it tells me that I get 4.755 hours. So it'll take 4.755 hours for the amount of bacteria to triple. All right, so you are allowed to skip some steps if you see that it's the rate is proportional to the initial amount, and you can think of the PERT formula. But all of this work down here, notice none of this is calculus. The only calculus we did was right here to get us to this point. So let's look at 1 or 2 more and go through this one. Okay, why don't you try this one? This time they give you the differential equation, but notice dy dt is proportional to y itself. So this is telling you that the population y is growing in a rate that's proportional to itself. Okay, so try that one, and then I'll go over it in just a second. All right. If you wanted to do the work, if you didn't see that the population y grows accordingly to the equation, you didn't realize that this was a value where it's proportional to itself, you would separate the variables and bring the y over here, do the antiderivative, and then take e to both sides. And remember that this a value is the same as e to the c. So I skipped that step. But then that leads me to the PERT formula, or the exponential model. And now, do I know if this is growth or not? Well, the population is doubling, so it is growing. If it was decreasing, it would be a different value. So that tells me that my rate, my k value, has to be positive. So if there are any negative values here, I could cross them out. That would eliminate one choice. Well, what do we do? Well, now the population doubles. The initial population is A. So if the population doubles, then our population would be 2A. And that's what's going to go right here for y. 2A is equal to A e to the kt. But we know that it doubles every 10 years. So actually, instead of putting t here, I'm going to put a 10. Remember, the a's reduce out. and then I'll take the natural log of both sides. I keep flipping that around, but whatever. And then divide by 10. And notice they asked for find the k value. So all I have to do is take the natural log of 2, divide that by 10, and I get 0.693 equals k, and that is A. All right, last one. This one you also might realize. Now I'll give you a hint here. So you might realize that this is dy dx is proportional to itself. So dy is proportional to y, which means this is an exponential model. So since we know that, you can actually automatically reduce out anything that doesn't have an e to the x in it. So I can get rid of this one. And you could even get rid of these two because there's a plus value, and we don't have the plus value. The PERT formula looks like this. So our answer has to be something in this form, which means it's either going to be A or B. So we narrowed it down just by knowing and recognizing the pattern. But if you didn't recognize the pattern, let's go ahead and split this up. Okay, bring the y over to the other side. Leave the 4. That's a constant. And then why don't you guys go ahead and work through this? They give us the initial condition here. And I'll come back and show you in a second. All right, so we take the antiderivative of 1 over y, we get ln of y. We take the antiderivative of 4, we get 4x plus c. Now we use the initial condition, plug in 0, plug in 4, and I get c equals the ln of 4. So now we go back to the spot where c was first present, and we're going to plug in what c is equal to. And then we're going to simplify. So I'll take, and I have to solve for y. So I got to raise both sides of the power of e. So I'm left with the natural log of y equals, and then this is where we're going to use that property. If you recognize it, you could skip this step, right? Addition means multiplication with the same base e. And then notice what happens. E and ln of 4 is just the value. And you might notice that this number right here, the natural log of 4, that's always going to be the initial amount present. So now the question is, what value do I use? I know my answer is right here, A, right? It's present, 4 times e to the 4x. But I also want to make point that notice this is a positive 4. So if I plugged in 0, e to the 0 is 1, and that times 4. So that means that this has to be the positive value. You don't have to write the positive there. But there is our answer, A. If you recognize the shortcut, you could potentially do this in your head without showing it any work. Okay? Here's your homework tonight. It's the 9 practice problems in the textbook, Practice AP Problems, page 553, 1 through 9. The answers will be posted in Schoology, so you can check your work as you go. When you're done, submit this to Schoology. Have a wonderful day. Adios.